So last lecture we talked about using Chimera in order to look at protein structures, and hopefully you've got a good sense of what a protein structure is. And so now we're going to get into using Python to analyze these types of structures, and we're going to use a BioPython, which includes a module for reading, writing, and analyzing PDB files. So if you haven't yet, you can install BioPython using Conda, and then once you manage to do that, you should be able to import it into your interpreter. So if you haven't installed it, you'll get an error, and so BioPython actually contains a large number of different modules. Some of these are useful for analyzing sequence data. Some of these are useful for doing pairwise alignments, and they are organized into different subunits. And so the subunit that we're going to use is called PDB. So PDB contains all of the different functions and classes that are useful for analyzing PDB files. So now that we've installed it, we can import this into the interpreter, and now we can start to worry about reading in a PDB file. So the class that you want to create, so we want to create this object using this class definition, and it's called Pdb Parser. So this class is designed in order to read in PDB files. So PDB files, as I talked about before, are kind of complicated, poorly defined file structures, and so there's actually a lot of effort that went into creating this to read in PDB files. And then we need to open the file, and let's see, have I not downloaded this yet? So we'll also re-download this PDB file. And now we'll try again to read it. Where am I? I'm in example data. So you'll notice now I have this PDB file in the directory I'm in, and then I can go ahead and run this command. So the way this command works is I give it the name of the PDB structure that I'm reading in. So this can be whatever you want, and then this just needs to be the name of the file that contains the data. And so we've managed to read in the PDB file, and we've created this structure object. So this structure object is a class called structure. And if we look at the attributes and the methods available to it, we can see this here. So I've gone ahead and highlighted in red some of the important ones that we are going to use throughout this lecture. So child list is a way to look at all the children of the structure, and we'll get into that in a second. And then there's also methods in order to get some of the lower level objects, the atoms, the chains, and the residues, using these what are called iterators. So they're a way to loop through all of the residues within the structure. ID tells you the name of the ID of whatever we're looking at, and then parent is the parent object. So to understand how a structure object is organized, these PDB files are organized into a tree-like hierarchical structure, and this is called the SMCRA, or SMCRA. And so the highest level is the structure, and so each PDB contains a single structure type object. And then below the structure is what's called a model. So typically there's only one model for PDB, especially when you're talking about protein crystal structures. So this is like a shape of the object. And so the idea is that you can have a protein have multiple different shapes depending on things like whether it's bound to a ligand or not. So like when a ligand binds a protein, it might subtly change the shape of the object. And so PDB can actually hold multiple different models. But for protein crystals, a protein crystal, because it's this rigid object, will only contain one particular type of model. If you had a PDB file that was created through other approaches, experimental approaches like NMR, then there could be multiple models per structure. But for everything that we're going to cover in this class, there's only going to be one model for each structure. And then below the model is a chain, and there's often multiple chains per model. And so this is each polypeptide is its own chain. So we saw this before when we were looking in the chimera, that typically these protein complexes can be made of heteromers or dimers or whatever. Very rarely is there only a single monomer within a protein file. And that's just because proteins like to actually physically interact with other proteins. Residue, so residue is at the level of the amino acid. So a single polypeptide chain will often contain maybe 300 amino acids. So a residue belongs to a specific chain, and then atoms belong to specific residues. So residues are made up of carbons, hydrogens, oxygens, nitrogens, and so this atom level information is the level of detail of that. And so this diagram right here just kind of shows you how the relationship goes. So the structure is at the top, and the structure is the parent of the model. So the model is a child of the structure, and that kind of defines the relationship when we're talking about parent-child. So a model belongs to a structure, and there can be multiple models that belong to a structure. A chain then belongs to a model, so the chain is the chain is the child of the model, and then the chain is the parent of the residue. The residue is the child of the chain, and the residue is the parent of the atom, and then the atom is the child of the residue. So let's see how this works. So structure, we have our structure object, and we've said that it has children, which are models. And so if you want to look at the children, it's easiest often to do that using this child list attribute. So if we simply do that, we see we have a list of all of the model objects that belong to the structure. And like I said, there's only one. There's also this dictionary, so you can use either one of them. It's kind of whatever you're comfortable with. So the dictionary is the ID is the key of the dictionary, and then the model object is the value of the dictionary. So either of these work if you wanted to try to access the children. It's just whatever you prefer, working with lists or dictionaries. So let us store this as a new variable. So now we have the model, and we can see that the model is a new type of object called model. Many of the attributes and methods are the same as the model object, so it still has this child list, it still has this parent, it still has the ability to get chains, get residues, get atoms. So all of those are still available, but one thing you'll notice that it no longer has the ability to get models, which should make a bunch of sense. So the structure object has the ability to get all the models, but a model doesn't belong to itself, and so it doesn't make sense for the model to be able to get the models. So these functions work by only looking below in the tree, lower in the tree. Those are the types of objects that it can return with this iterator. So the model, now if we look at the parent is the structure object, and so this is a way to get a pointer to that structure object if we wanted it. And then the child list, we can look at the children of the model, and so now we see that there are a bunch of chains. So we saw before that there is 5 chains. 5 chains of the glutamate-gated chloride receptor, and then there was a total of 10 chains, 5 for the heavy antibody, and then 5 for the lighter antibody chain. So all 15 chains that we saw within that chimera are all present now within here. So if we wanted to get to a chain, we could do something like this, and we'll just store this as equal to chain. So chain, again, has many of the same functions and attributes, but you can no longer get chain. So get chain is no longer an option, but you can get the atoms and you can get the residues that belong to this. You can look at the children. So chain.child list. And so these are all the residues that belong to this chain. So you see that there's a lot of residues that belong to this chain, and that makes sense. Typically there's like 300 amino acids that belong to a given polypeptide. And so each of these residues has a name. So phenylalanine, valine, leucine. So you should recognize many of these. These are amino acids, and you have a number, so 340, so you can see these kind of like go in order, 301, 302, 303. So you can use this to figure out the sequence of this polypeptide chain. But it's also important to note that ligands will also belong to a chain. So we have these following things. So these are all additional molecules that are not part of the polypeptide chain that also belong to this chain. So two of the ivermectins belong to this. The glutamate, one of the glutamates, that the glutamic acids that is actually the neurotransmitter part that binds to this protein, belongs to this chain, as well as some of the fatty acid molecules as well. So one of the ways that you can distinguish between the polypeptide chain and the ligands is that these ligands always have this additional het value. So you can see that there's glutamates within the polypeptide, because glutamate is also an amino acid, but the glutamates that belong to this polypeptide chain do not have a het value, and so the glutamate that represents the neurotransmitter does, and same with the ivermectins and these other things. So that can be a useful way to distinguish between whether or not a residue belongs to a polypeptide or a residue is actually a ligand. And then we can keep going down. So let's look at this residue, and then this residue has this ability to get atoms. So you still have the ability to get atoms. Where did that go? Get atoms right here. But it no longer has the ability to get residues, chains, models, etc. It also has a parent. So you can see this particular residue belongs to chain A, and it also has a child list, so you can see all of the atoms that belong to it. So the serine, so if we looked up a serine, serine looks something like this. So you have the backbone, and so you have the backbone of the molecule, but you can notice that there's 1, 2, 3 carbon atoms. So there's 1, 2, 3 carbon atoms right here. There are, multiple oxygens. So let me see if I can see a serine. This will make it clearer. So it's important to note that the subunit of the building block of amino acid, when you make a polypeptide chain and you covalently bond two amino acids together, you end up having you lose a water molecule. So you're going to lose H2O. So you're going to lose two of these hydrogen atoms and then one of these oxygen atoms. So that can be a little bit confusing when you're trying to compare. So we are looking at a serine. So this right here. So this is the backbone right here, but you're going to lose one of these oxygens. So that's why you only have two of the oxygens. You have one right here and then one right here. And then you're going to have a nitrogen atom right here, and then you don't have any of these hydrogens, and again that's because the hydrogen atoms are not present in the PDB file because they're too small to actually deflect. So you should actually spend some time and make sure that you get used to understanding exactly which atoms you expect to see within a polypeptide chain, because that I think will be useful for helping you understand. So there's the backbone, so the backbone which is the same in all of the different amino acids, and then there's the side chain that will be specific for each residue that you use. So now let's finally look at the atom. And so the atom actually has a bunch of new attributes that you don't see before. And one of the main reasons that the atom is different than the residue and the chain, etc., is because this is the only thing that has a physical position. So this physical position can be accessed through, what is it, cord. So you know, the crystal structure tells you the position of all the different residues, but the residue doesn't have the position. It's the atoms within the residue that actually have these positions. And so if you want to get to the positional information and understand where in the protein it is and how far away it is from certain things, then you have to reach down to the actual atom level in order to do that. And so this atom right here, the position in the XYZ is given in this NumPy array right here. So, you know, as I said before, many of these libraries use NumPy to build upon. This is just another example of how you use NumPy to hold all these different coordinates. So we've gotten down to residue. And just to talk a little bit, so if you want to get the name, the type of residue it is, res name is what holds that. If you want to know the coordinate, that's a little bit tricky, so you can use this ID, residue, this ID attribute, and so that holds information including the position. So that is the position of the residue in terms of like the coordinates. Atoms, so let's do so we have two different elements. So if we want to know the element, we use that. If we want to use the ID, we use that attribute. So you notice that the element is carbon, but the ID is the Ca. So you know, each atom within a residue has to have its own unique name, and so typically it follows this naming scheme where so for example, for alanine, you have this alpha carbon right here. You have a nitrogen because there's only one nitrogen typically. You don't give this one a separate name. This carbon right here is one of them, and then you can have something like a beta carbon, and then other names as well. So you know, you get to this like alpha, beta, gamma, just to distinguish between the different carbons. So hopefully that part makes sense. The final thing that's useful to talk about with atoms is two more things that we'll talk about with atoms. So does an atom, how far apart are two atoms? So, you know, these two atoms have two different coordinates. And so you might want to know how far apart they are. So you'd have to do something like Pythagorean's theorem in order to do that, where you subtract these values, square it, subtract these, square it, subtract these values, square it. But they have overloaded the subtraction magic method so that you can simply just use subtraction to figure out the physical distance between them. So that's something very useful to know. And then if you want to know if two atoms belong to the same residue, this is where the parent function can be very useful. And you know, you can just use the comparison operator to see if these parents are the same. All right, the final thing that we're going to talk about in this section is other ways to access the atom's residues. So we talked before that, for example, structure has all of these different ways to access the models, the chains, the residues, the atoms. And so this is just an iterator, and so the way you use that is something like this. You know, so this has printed every single residue that is within the structure. You know, you could also do this with model. So we've also, you know, stored a model or a chain, for example. And so you could also do that with chain. So for residue and chain dot get residues. And then you can print all of the residues that belong to a specific chain. So one thing that's important to remember, so let's just make a little counter right here. So if we go through and count all the residues that are within the structure, there's 3,691. But if we count all of the residues within the chain, there's only 345. So one of the things this get residues does is that it only returns the residues that belong to a particular object. So the structure contains all of the residues within the entire file, where the chain only includes the residues that are part of that chain. So hopefully that makes sense. All right, so now we have the basics of how to go through a PDB file and start to get information about the residues, the atoms, the positions of the atoms. And so now we'll kind of work on exercises that explore how we can use that to get things like distances between residues, etc.